In this video, we're going to work a bunch of problems related to percent composition by either mass or just in general, as well as determining the empirical formula. So you can use the percent composition by mass or just in general to get to the empirical formula. All right, let's get started. Tin exists in Earth's crust as SnO2. Calculate the percent composition by mass of tin and oxygen in SnO2. All right, so what we want to do is you first look at SnO2. What is the percent composition just in general? So like by atom, or not the percent, just what is the ratio of oxygen to tin? It's 2 to 1. 2 parts oxygen to 1 part tin. So all we need to do to get the percent composition by mass is say, what is the mass of an oxygen atom? Multiply that times 2, and then take the ratio of that to the mass of one tin atom. And then we would have a ratio comparing the percent composition by mass of the different elements in this compound. And so if the percent of composition by mass of tin, we'll just take the molar mass of SnO2 and then the molar mass of tin. And you can think about this. What you have is, so grams of tin per mole of tin for 1 mole. Grams of SnO2 per 1 mole. And these end up, if you do this division, you get, this is just, we're looking at the units. Okay, a mole of tin and a mole of SnO2, tin oxide, that's the same thing. It's like saying you have 1 dozen of something and another dozen of something. That's the exact same thing. So now we've got this grams here. Now it's grams per mole, but a mole and a molecule are interchangeable. Like a mole is just a scaled up version of a molecule. If we computed the mass of 1 atom of tin and the mass of 1 molecule or compound, I think this is a ionic compound of SnO2, we're going to get, we'd have smaller values here, but we get the same ratio because these are just scaled up by the same number. Mole, you see how that works? We divide the molar masses to get the percent composition by mass. Technically, we're really wanting to divide the mass of 1 tin atom by the mass of 1 compound of SnO2. But if we do the molar mass, it's the same result. So the percent composition by mass of oxygen, we would just say 2 times the molar mass of oxygen over the molar mass of SnO2, because there's 2 oxygens. So let's do that. What is the molar mass of tin? 118.71. Okay, what is the molar mass of oxygen? 15.999. Okay, and now the molar mass of SnO2 is 150.708, 150.71. All right, so the percent composition by mass of tin is, And I'm not going to write out the units. I showed you how the units work. Over, and then we'll just add, we'll multiply by 100 and add the percent. So 78.8%. Okay, now the oxygen, 2 times over okay 21.2%. And we could have just subtracted 100 from this, because if 78.8% of this is 10, well, the rest of that must be oxygen. But if you had more than 2 atoms, then this is the process we would do. For many years, chloroform was used as an inhalation anesthetic in spite of the fact that it is also a toxic substance that may cause severe liver, kidney, and heart damage. Calculate the percent composition by mass of this compound. All right, I'm not sure what they're asking, just the percent composition by mass. I guess they mean the percent composition by mass of carbon and hydrogen and chlorine. So let's do that. We're just going to get the molar mass of this compound, then the molar masses of each element, and use those to calculate the percentages. So what is the molar mass of carbon? 12.011. Okay, the molar mass of hydrogen, 1.008. And then the molar mass of chlorine, 35.45. Okay, and then the molar mass of CHCl3 is 12.011 plus 1.008 plus 3 times 35.45. Okay. $119.37. This is grams per mole. All right, so the percent of carbon is and I'm not going to put the units. Well, actually, let me just put the units to show you. I went through it in the previous problem, but we'll do it once. I'll do the units once here. So we've got grams of carbon per 1 mole of carbon. Okay. Well, we're doing the molar mass of carbon divided by the molar mass of CHCl3. Okay, so we've got grams of carbon per 1 mole of carbon divided by grams CHCl3 per 1 mole of CHCl3. All right, so grams of carbon per 1 mole of carbon times, and then 1 mole of CHCl3 per 119 grams CHCl3. Okay, a mole of carbon and a mole of this molecule or compound, it's the same thing. It's like saying you have 1 dozen eggs and 1 dozen something else. As far as the like we're dividing numbers here. These are the same. These are 2 moles. Again, same idea. A gram of carbon and a gram of that weighs, and a gram of CHCl3 that weighs the same thing. It's like saying what weighs more, a pound of bricks or a pound of feathers? It's the same weight. They're both a pound. This cancels. Now we're calculating the ratio of 1 mole, the weight in grams of 1 mole of carbon to 1 mole of this compound. But because it's a mole, we know it's also the same thing as calculating the weight of 1 atom of carbon to 1 molecule of this compound. And if we're dealing with Cl3, we would just multiply this times 3, because there would be 3 Cl3s. Mole is just a scaled up version of a molecule. So it's the same. So it's giving us the same result. If we use a mole, the weight, the grams per mole or grams per atom, it's the same thing. So what we get is 10%, 10.1% carbon. Okay, so now the percent hydrogen, take the molar mass of hydrogen divided by the molar mass of CHCl3. So we've got 1.008 divided by 119.37. .84% hydrogen. So that's interesting. Hydrogen is so light, it's as far as just by atom, hydrogen would be what, 1 to 5. The ratio of that would be the ratio of hydrogen atoms to all the atoms in the molecule. 1 to 5, right? Because it's 1 part hydrogen to 5 parts everything else, or 1 to 4, I guess. But as far as by mass goes, it's only 0.84%. Okay, so now the percent chlorine. All right, but we want to take 3 times the molar mass of chlorine. Right? There's 3. So 89.1. Okay, and then just to show you, so 10.1 plus 0.84 plus 89.1, 100, approximately 100. All right, peroxyacyl nitrate is one of the components of smog. It is a compound of carbon, hydrogen, nitrogen, and oxygen. Determine the percent composition of oxygen and the empirical formula from the following percent composition by mass. What is its molecular formula given that its molar mass is about 120 grams? All right, the empirical formula, if you remember, it's strictly stating the ratios of the elements in the substance. So like if you've got, like you have H2O, it's 2 parts oxygen, or no, 2 parts hydrogen to 1 part oxygen, not by mass. So H2O, that's the molecular formula and the empirical formula. But if you had H4O2, I'm not sure if that's a real molecule, but this would be the molecular formula. And then if this was a molecule, right, you could have a molecule of H4O2, but the empirical formula of this would be H2O. And I think it's better, let's use like okay, might be a better example. It's like C6H12O6. This is like a single molecule. That's the molecular formula, but the empirical formula is, so you divide by 6. It's like 1 part carbon to 2 parts hydrogen to 1 part oxygen. Not by mass, we're talking just by molecule here. That's the empirical formula for this. This right here is 1 part carbon to 2 parts hydrogen to 1 part oxygen, right? That's why this molecule's empirical formula. But if you're talking about an actual molecule, it's not just one molecule doesn't have 1 carbon, 2 hydrogens, and 1 oxygen. The molecule has 6 carbons, 12 hydrogens, and 6 oxygens. Okay, so we're trying to determine the empirical formula for this peroxyacyl nitrate, and if we're given the percent composition by mass of everything. It only gives us carbon, hydrogen, and nitrogen, but we can just take, once we can take 100% minus this, and this to get the oxygen percent. So if we have the percent composition by mass, how can we get to the empirical formula? Well, we want to determine the ratios of the number of molecules. So we want to get out of mass and get to moles, right? Moles and atoms is the same thing as when you talk about percentages, at least ratios. So if we can get to the percent composition as far as moles, then we can just take that. Then we have everything we need. We just take those ratios and use those numbers to get these whole numbers. I'll show you how to do that. Once you've got the percent as far as moles, then you can easily determine the empirical formula. And then I'll also show you, once you have the empirical formula, you can determine the molecular formula easily if you know like an approximate estimate for what the molar mass of the compound is. And I'll show you how that works. But, well, okay, first of all, let's say let's find out the percent composition of oxygen. So 100 minus 19.8 minus 2.5 minus 66.1%. So percent oxygen by mass. Okay, so we just want to find out the atom percent, the mole percent. And so since we're dealing with percents, we can just we can assume we've got 100 grams of this substance. And I'm not going to use 120. Say we've got 100 grams of this PAN. Okay, it doesn't matter what we choose. You could say, well, why don't we choose 120 because 100 is easier to work with. We're dealing with ratios and percentages. So the percent by mass of these elements in 100 grams of this component of this PAN is the exact same as if it was 120 grams. The percent composition, the percent, like the ratio of moles or the ratio of atoms is the exact same no matter what. The empirical formula doesn't change if you have 100 grams or 120 grams. So we could just say we've got 100 grams. Okay. So that means that we've got 19.8 grams of carbon. All right, what is the molar mass of carbon? 12.011. So 12.011 grams of carbon per 1 mole of carbon. So 19.8 divided by 12.011, 1.65 moles of carbon. Okay, these cancel. In 100 grams. In 100 grams of this PAN, there's 1.65 moles of carbon. All right? How many moles of hydrogen are there? Okay, molar mass of hydrogen, 1.008. Okay. .48. Okay, so now what about nitrogen? Grams. Molar mass of nitrogen, 14.007. Okay. So .828. Okay, and now what about oxygen? So the molar mass of oxygen, 15.999. .13. All right, so now we have the number of moles of each of these elements in 100 grams of PAN. And you might be saying, well, we have a problem because how do we know the total number of moles in 100 grams of PAN? We can't just add these up because, well, it depends. What do we have? Do we have 3 carbons? Do we have 4 hydrogens? We don't need that. This is all we have to do. So take the smallest value and divide everything by that. So we'll have carbon, hydrogen, nitrogen, oxygen. Okay, so carbon. Okay, 1.65 divided by 0.828. 2. So 2. Okay, hydrogen, do 2.48 divided by 0.828. 3. Okay, now let's do, so nitrogen 0.828 divided by 0.828 is just 1. And then oxygen 4.13 divided by 0.828. 5. Okay, there you go. So we've got nice whole numbers here. So what this tells us is we can write out our empirical formula. C2H3NO5. Great. Now, again, this doesn't tell us that a molecule of PAN is this. We just know, this is the empirical formula. We know that this PAN is 2 parts carbon to 3 parts hydrogen to 1 part nitrogen to 5 parts oxygen. So if we want to know its molecular formula, and we know its molar mass is about 120, it doesn't have to be exact. This is what we can do. We can take this molar mass of this empirical formula, and we know that if we divide the molar mass of the actual molecule by the empirical molar mass, it's going to be it has to be close to a whole number. So if it's 2, then we just multiply this by 2 to get the molecular formula. So, okay, so the molar mass of C2H3NO5 is what? So, okay, so we got our molar masses of the individual elements here. So 2 times 12.011 plus 3 times plus 14.007 plus 5 times 15.999. 121.05 it was. Okay, so this is also the molecular formula. It doesn't matter that it's not exactly 120. They said about. Because we know for a fact that if you took the precise exact molar mass of whatever PAN is and divided that by the precise exact molar mass of the empirical formula, well, you know that because you have the formula, but you're determining this experimentally. Let's say this 120. If this was the exact amount, then you divide the two. You have to get a whole number. So we know that this is the empirical form. This is the molecular formula as well. Tin-2 fluoride is often added to toothpaste as an ingredient to prevent tooth decay. What is the mass of F in grams and 24.6 grams of the compound? Okay, so we've got 24.6 grams of the compound. All right. Now we want to get to units of F. So we can convert this to moles, and then once we've got the moles of SNF2, we can say what? We can say for every 1 mole of SNF2, you've got 2 moles of F. Because a mole, you can think of a mole as just it's like a dozen. If you have a mole of SNF2, you've got, think about it like saying you've got a dozen SNF2s. Well, in a dozen SNF2s, how many Fs do you have? You've got 2 dozen, right? But mole, we're just using mole instead of dozen. So we need the molar mass of SNF2. Okay, the atomic weight of tin is 118.71. Plus 2 times the atomic weight of fluorine, 18.998. Okay, so $156.71. Well, let's put it. Grams Okay, so we can say we've got 156 2 per 1 mole SNF2. So now we've got the moles in this 24.6 grams of the compound. We have the number of moles there are. So think about what I just said about the dozen. If we had a dozen SNF2s, like we can just say, okay, we want to get to moles of fluorine. So we know that just looking at this compound, for every 1 mole of SNF2 and put moles of SNF2 in the denominator, you've got 2 moles of fluorine. All right, so now we're in moles of fluorine. Are we done? No, they're asking us for the mass of fluorine in grams. So how do we convert this to grams? Just use the molar mass of fluorine, and that was 18.998. So it was 18.998 grams of fluorine for every 1 mole of fluorine. We had 24.6 times 2 times divided by 156.71. 5.96 grams of fluorine. Okay, think about what this is saying. In 24.6 grams of this, of tin 2 fluoride, 5.96 grams are fluorine. Interesting. What is the empirical formula of the compound with the following composition? 18.4% carbon, 21.5% nitrogen, 60.1% potassium. So I wasn't sure if they're talking about percent by mass or what here, or just percent by atom. I looked into it, and I think they're talking about percent by mass. But if it was percent by atom, then you could just go straight to saying, okay, for carbon, 18.4 divided by 18.4. For nitrogen, 21.5 divided by 21.5, or divided by 18.4. For potassium, 60.1 divided by 18.4, and then go from there. But I believe they're talking about by mass here. So we assume we've got 100 grams of whatever this is. So that means that we've got 18.4 grams of carbon, and moles, that is. So 12.011 grams per mole. Okay, 1.53 moles of carbon. Okay. (21.5) in this 100 grams, we've got 21.5 grams of nitrogen. 14.007. So per 1 mole of nitrogen. So 1.53. Okay, and then 1 grams. 39.098. So 39.098 grams of potassium per 1. Okay, so 60.1 divided by 39.098, 1.54. All right, so now we have 100 grams of this compound. So in 100 grams of this compound, we have this many moles of each atom. It's all the same number, right? You divide, so it's the empirical formula is KCN. Okay, the empirical formula of a compound is CH. If the molar mass of this compound is about 78 grams, what is its molecular formula? All right, so what is the molar mass of the empirical formula? So 12.011. So we've got plus hydrogen 1.008. So 13.02 grams of, okay, so we know that this is the empirical formula, for the actual compound. The molar mass of the actual compound has to be some whole number multiple of the empirical formula molar mass. It has to be. Think about it. Okay, and so even if we experience, when they're saying about here, is because they're experimentally determining it. So it's going to be approximately this. So that's all we need. If we divide, the molar mass is 78 grams per mole. So 78 divided by 13.02, 5.99. So 6. So what we do is, this is the empirical formula, just multiply it by 6. So it's going to be C6H6 is the molecular formula. Okay, monosodium glutamate, MSG, a food flavor enhancer, has been blamed for Chinese restaurant syndrome, the symptoms of which are headaches and chest pains. MSG has the following composition by mass. Okay, what is its molecular formula if the molar mass is about 169 grams? So same process, just a bigger problem. Okay, 100 grams of, we take, this is the percent by mass, so assume we have 100 grams. It doesn't matter what, you can assume whatever you want, because we're dealing with just ratios here. All right, so if we have 100 grams of the substance, then that means that we have 35.51 grams of carbon. And then carbon, the molar mass of carbon is 12.011. So 12.011 grams of carbon per mole of carbon. Two point 2.96 moles of carbon in this 100 grams of the MSG. All right, so we've got 4.77 grams of hydrogen, and then hydrogen molar mass is 1.008. So 1.008 grams of hydrogen for every 1 mole of hydrogen. Okay. .73 moles of hydrogen. Okay, now we've got 37.85 grams of oxygen. Molar mass of oxygen is 15.999. 15.999 grams of oxygen for every 1 mole of oxygen. Okay. .37. moles of oxygen. Okay, now 8.29 grams of nitrogen. All right, molar mass of nitrogen is 14.007. Grams of nitrogen for every 1 mole of nitrogen. Okay. .59 moles of nitrogen. All right, now sodium, 13.6 grams of sodium. Okay, sodium is 22.99. 22.99 grams of sodium for every 1 mole of sodium. Okay. .59. All right. So in 100 grams of this MSG, we have this many moles of each of these atoms. And actually, the more I'm thinking about it, if we come back here, I guess at this step, we could determine the percent by atom. Yeah, because we've got 100 grams of this, we have a certain amount of this substance, and then we know the total number of moles. So yeah, you could determine the percent. You would multiply this times 2. It's 1.65 total grams of carbon in this substance here. Yeah, so just trying. I don't mean to confuse you. I'm not a chemist. I just know how to work these problems really well. So just think about what I'm saying. Think about it for yourself. All right. So we'll have carbon, hydrogen, oxygen, nitrogen, sodium. So what is the smallest amongst these? It's the 0.59. So this is going to be a 1 and this is going to be a 1. Let's take 2.96 divided by 0.59. 5. Okay, let's take 4.73 divided by 0.59. 8. All right, now let's take 2.37 divided by 0.59. 4. And then this will be 0.59 divided by 0.59, 0.59 divided by 0.59. All right, so we have 5 parts carbon to 8 parts hydrogen to 4 parts oxygen to 1 part nitrogen to 1 part sodium. So the empirical formula is great. Now we need to determine the molecular formula. We need to find the empirical formula molar mass and compare it to their approximation for the molar mass of the actual molecule. So we do 5 times 12.011 plus 8 times 1.008 plus 4 times 15.999 plus 14.007 plus 169. Okay, So this is also the molecular formula, but let's say it was whatever 169 times 2 is. Then you would divide, let's say this was like 300 something. We would divide that by 169 and we would see it's 2. Then to get the molecular formula, you just multiply this times 2. It would be C10H16O8 N2 Na2.